Continuing the lecture on the multiplication principle, going to work some examples here. I'll start you off with something that's pretty simple. If a married couple is planning to have 2 children, how many possible outcomes are possible if the order of the births are taken into account? Now you could write out the possibilities, and it's really not that difficult to do. You could write out, boy, 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 girl, girl, boy, girl, girl. But if you have more than 2 children, then it might get a little bit tougher. So let me just go ahead and show you how you would do this. The first operation would be, the result of the first child, and that has 2 possible outcomes. And then the second operation would be the result of the second child, and repetition would be allowed in this case because you could have a boy and a boy or a girl and a girl. So we would have 2 possible outcomes for that. And so if you take the number of ways the first operation can be done, number of ways times the number of ways the second operation can be done, that gives you 4 possible outcomes. Now again, you could just simply list them, and it's pretty simple to do. But let me show you what happens if we have more than 2 children and we extend this problem a little. So if we extended the problem to 3 children, then you would have 2 times 2 times 2, or 8 possibilities. If we extended it to 4 children, you'd have 2 times 2 times 2 times 2, or 2 to the 4th, or 16 possibilities. And then if we did 5 children, you would actually end up with 2 to the 5th, or 32 possibilities. So actually, having multiple children, or tossing multiple coins, or answering multiple true-false questions, they follow a similar pattern. So if you tossed 3 coins and wanted to know the number of ways they could land, it would be just like having 3 kids and wanting to know the number of ways they could be born. So you would do the same thing. There's 2 possible outcomes on the first coin, heads or tails, 2 possible outcomes on the second coin, heads or tails, and 2 possible outcomes on the third coin, heads or tails. So that would be 2 times 2 times 2 is 8. And if you tossed 5 coins and wanted to know how many ways they could land, that would just be the 2 to the 5th, like I did up there on that example with the children, which would be 32. And then if you wanted to say, change this to how many outcomes are possible if you answer 3 true-false questions, well, you could answer the first question true or false, so there's 2 possibilities. You could answer the second question true or false, and you could answer the third question true or false. So 2 times 2 times 2 would give you 8 possibilities. And if you had 5 true-false questions, there's 32 different answer sheets that one could turn in. This text here regarding the binary code is just something extra that I threw in. So I'll just slowly scroll through it, and you can read it. And if you need to, you can pause the video if you want to. But it's just a little bit of extra, no pun intended, that you can look at here, and you can see that computer security also uses some of these counting techniques. So let's say you go to your closet and you find that you only have 2 clean shirts, 3 clean pants, 3 decent pairs of shoes, and 4 belts. And you want to know how many outfits you can put together. So there's 2 ways to choose the shirt, there's 3 ways to choose the pants, 3 ways to choose the shoes, 4 ways to choose the belt. So you just multiply that and you get 72. Now that didn't allow any repetition. The next example does though. How many possible 10-digit phone numbers are there under the following conditions? First of all, no restriction. So the numbers can be 0 to 9, and that's 10 digits, so that's 10 possibilities. So that means there would be 10 ways for the first digit, 10 ways for the second digit, 10 ways for the third digit, and so on, all the way out to the 10th digit. And so that would give you 10 to the 10 possibilities, which would actually be 10 million. And I see I'm missing a 0 here, so let me put that in there for you. So it should be 10 million. And then if we put a restriction on the first number and said the first number could not be a 0 or 1, then all that would change is that the first number would only have 8 possibilities, but the other numbers would still be back to 10. So if you multiplied that out, you would get 8 times 10 to the 9th, which is actually 8 million possibilities. So actually, these are just maximum numbers that could be assigned, but actually the actual numbers that would be available would be probably much less than that, because you couldn't start a number out with 911 or 411 or something like that, since they're used for other things. Suppose a debit card has a PIN consisting of 4 digits. How many possible codes can be selected if there are no restrictions on the selection? So no restriction means you can allow repetition. So that means, you can choose from the 10 digits. So there's 10 digits you can choose for the first entry, 10 digits for the second entry, 10 digits for the third entry, and 10 digits for the fourth entry. So that gives you 10,000 options. Now, if digits cannot be repeated, then that would give you 10 digits for the first entry, but since you can't use what you used here for the second entry, that would only leave you 9 digits for the second entry. And since you can't use what you used in the first 2 entries for the third digit, that would leave you 8 digits for the third choice, and then likewise 7 digits for the last choice. And so when you multiply that out, you get 5,040. This third example is a little bit different. It says how many possible codes can be selected if adjacent digits must be different. So let me try to show you down here in this little box why I got the answer that I got. So we know the first digit can be any of the 10 digits 0 to 9. Now let's just pick a random number for the first digit. Let's suppose we chose 7 for our first digit. Then we know the second digit cannot be 7 because the second digit would be adjacent to this. So that would leave us 9 choices. Now suppose we chose a 5 for our second digit. Then the third digit cannot be a 5, but it can be a 7 now because it's not adjacent to the first digit. So the only number it couldn't be would be the 5, so that would leave us 9 choices for the third digit. And then suppose we chose 4 for the third digit. Then the fourth digit cannot be a 4, but it can be any other number, so that leaves us 9 choices again. So that tells us the first digit has 10 choices, the second digit has 9 choices, the third digit we have 9 choices, and the fourth digit we have 9 choices. So the answer would be 10 times 9 times 9 times 9, which is 7,290. So let's say you toss 4 coins. Then we know, we saw this earlier, there's 2 ways each coin could land. So 2 times 2 times 2 times 2 would be the result, 16. Suppose you toss 2 6-sided die. Well, we know the first die can land 6 ways, and repetition's allowed because the second die could land 6 ways as well. So we get 6 times 6 equals 36. What if we tossed 3 6-sided die? Well, then they could land 6 times 6 times 6 because each dice could land 6 ways. So you'd have 216 ways they could land. Now, what if you toss some weird dice like a 4-sided die, a 5-sided die, and a 6-sided die, and want to know how many ways they could land? Well, we know the 4-sided die could land 4 ways, the 5-sided die could land 5 ways, and there's 6 ways the 6-sided die could land. So it'd be 4 times 5 times 6. Now, let's take a look at example 8 here. How many different license plates can be manufactured if they must consist of exactly 6 characters? And when I say characters, that's letters or digits. And so that would be 36 characters total, 26 letters and 10 digits. So each space can be any of the 36 characters because there's no restrictions on this. So 36 times 36 times 36 times 36 times 36 times 36. So there would be 36 to the 6th power possible license plates you could make with no restrictions. Okay, now what if we could have up to and including 6 characters? Well, now we have to say, okay, how many 1 character plates can be assigned? And so that would be 36. Because you could have anything from A to Z or 0 to 9, so that would be 36. And then how many 2 character plates can be assigned, like AB or AA or A1 or something like that? Well, there's 36 ways to choose the first character and 36 ways to choose the second character, so there's 36 squared ways. How many, that should say how many 3 character plates should be assigned, not 1. So 3 character plates, there can be 36 for the first character, 36 for the second character, 36 for the third character. So that would be 36 to the third. All right, and then you would continue this up to 6th. So basically, you would have 36 1-character plates, 36 squared 2-character plates, 36 cubed 3-character plates, 36 to the 4th power 4-character plates, 36 to the 5th power 5-character plates, and 36 to the 6th power 6-character plates. Now when I did that, I got over 2 billion possible plates. Okay, now if 2 billion is not enough, you could squeeze in one more. 36 to the 0 is 1, and this represents the plate with nothing on it. Some students don't understand why I add these together, but think of it like this. Let's say that one person was making these plates and they put all of the 1-character plates in, say, box 1. And then let's say another person was making these plates and they put all these plates in box 2. And then another person making these plates, they put them in box 3, and so forth. So you would have 6 boxes. So if you want to know the total number of plates, you would just add up the number of plates in the 6 boxes to get your total answer. So hopefully that helps you understand why I'm adding. Number 8 is kind of a repeat of something I've discussed earlier, so we won't spend a whole lot of time on it, but if you have 5 true-false questions, there's 2 times 2 times 2 times 2 times 2 ways to answer, or that's how many answer sheets you could turn in. If you have 5 multiple choice questions with 4 possible responses each question, then there would be 4 ways to answer each question. So you'd have 4 times 4 times 4 times 4 times 4, or 4 to the 5th possible answer sheets that could be turned in. And then if you had a mix of 3 true-false questions followed by 2 of these 4 response multiple choice questions, then each of the true-false questions, there would be 2 times 2 times 2 ways to answer them. And then the 2 multiple choice questions, there would be 4 times 4 ways to answer those. So that would be 2 cubed times 4 squared, which is 128 possible answer sheets they can turn in. The next one says, suppose you can order a pizza that has 4 options for sauce, 10 options for toppings, 3 options for crust in 2 different sizes. How many different pizzas can be ordered if you will only choose 1 sauce, 1 topping, 1 crust, and 1 size? Well, you know you have 4 sauces, 10 toppings to choose from, 3 options for crust to choose from, and 2 different sizes to choose from. So multiply all that together and you get 240 possible choices. The last one here says, how many different 3-letter code words can be created from the first 9 letters of the alphabet? Well, if there's no restrictions, then you can have repetition. So that means you can have a code word like AAA or BBC. So there's 9 choices for the first letter, 9 choices for the second letter, and 9 choices for the third letter, because we only have the first 9 letters of the alphabet that we can use. So that would be 729. Now, if you can't have repetition, then there's only 9 choices for the first letter, 8 choices for the second letter, because you can't use what you used here. And then there would be 7 choices for the third letter, because you can't use what you used here or here. So you'd have 9 times 8 times 7, or 504 code words possible in that case. Okay, so in the next video, I'm going to show you some examples of permutations and combinations and how they're used to calculate the number of elements in a set.